Welcome. See some familiar faces. I guess 2 days wasn't enough, and you get me for a third. All right, right now we're going to talk about Spirit, and in particular we're going to talk about Spirit X3. It's the next generation of Spirit. Spirit is a parsing and generation library in general. The V2 version of the library has both parsing and generation, where you can parse into an AST, and then you can later take a data structure, describe a grammar, and then output that AST data structure into a stream of some sort. Supports both text and binary type things. This discussion will be primarily about X3, which only has a parser and the parse side only, not the generation side. The library is a Boost library. It's written by Joel de Guzman. Joel works with Kiera Consulting. And we obviously then spend some time supporting this thing. Let's talk about why we have an X3. So X3 is the next generation of Spirit. It's using modern C++ 14 constructs internally. That's given us some things. One thing is hackable, simpler internal design. We're worried about trying to keep things easy inside. And V2 has become kind of a monster. It's a minimal code base, very few dependencies, compiles faster, like a lot faster. If you've ever used Spirit V2, expression templates can really cause a lot of compilation headaches, and the instantiations of all of these things will eventually slow your compilation down. We use some different tricks. We are using ADL tricks this time, and we'll see that in a little bit. Better error handling, a lot better error handling for plugging in your own error handlers. And we have an optimized attribute processing. So before, attribute processing was pretty good, actually really good, and now it's even better. So let's look at some concepts. It is a domain-specific embedded language. That is what it is. The domain is parsing. The embedded part is within C++ via expression templates. And the language is PEG. Which is parsing expression grammar. So it implements PEG. If you don't know what PEG is, that's fine. If you've seen an EBNF type grammar before, or really only any grammar definition, if you kind of squint your eyes, they almost all look the same, right? And so this is going to be for PEG. This, just give you some ad hoc parsing things. How many people have code that might look like this somewhere in your code base? Yeah, everybody. It's always everybody. So yeah, this is pretty normal, right? And it starts off innocent typically, but at some point it just falls apart, and you're trying to track down all kinds of state without a state machine using things that just really aren't the best way to take care of this type of a problem. So sometimes what you do is you say, oh, this might be better. I'm going to use a regex. Regex is like the most innocent thing when it starts because it's this long and you can read it until you realize it doesn't cover the things you want. And by the end of like the first week, you're the only one who can read it. And next month, you can't read it anymore. So regex is bad for generalized parsing, right? It's got its place, it does its thing, but it's not a parser. So we would like to do something else. So here's a PEG grammar for email. It's not really a PEG grammar for email, but it's going to be for us. We're going to deal with it as what email is. So a name, letters A through Z. There's one or more of those. And then there's a dot with more letters A through Z, one or more of them. And there are 0 or more of these things. That is going to be the name part. What is a host? Same type of pattern, dot, and followed by, in our case, it'll be either a com or an org or a net. And what is an email then? An email is a name at a host. This is easy to reason about, easy to understand. And it would be nice if we can write our code the same way. Underneath, we have now the Spirit X3 version of this. We're not able to put the operator plus at the end. We have to put it in the front. And so in order to take care of some of the rules within C++, we move some things around. So we have characters A through Z, one or more of those, followed by 0 or more, dot that's followed by one or more characters. This is a name. Looks a lot like this. What is a host? Well, same type of thing. We use bar instead of slash, com, org, net. And then what is an email? An email is a name followed by an @ sign followed by a host. This is readable. I know what it does. And the idea of writing, having a good parser, and specifically if you're going to write a DSEL, a domain-specific embedded language, is to write one where you can be declarative, right? And so now we have a declarative statement of what an email is. It's this thing. This now has created a parser for emails. This is what we want to get to. So let's talk a little bit about what parsers are. Parsers for us take some stream of values in. In this case, we have a float parser. It will parse this. If I give it foo, it will not parse that because the float parser doesn't like foo. I can compose these using what we would call a rule. So literal size parser followed by a float parser would be able to parse size space 42.5. So these composed together, we refer to these as rules. Rules, and in this case, we have size followed by big. The float parser portion of it fails. Rules can be composed with more parsers and more rules to create other rules. And the idea is that we want to create rules and parsers and then compose those and continue to compose them into larger and larger things. So now we have the original one that we had, which was literal size and a float parser, followed now by a comma, followed by color and a string. You would be able to parse this. All right, so parsing things is interesting, but typically when we're parsing something, we want data back out. We would like to do something with the data that came in and put it into a data structure that we can deal with. So 42.5, we parse this. We would like to get a double that is 42.5. This thing on the way out is called the synthesized attribute. This parser has synthesized this double for us. Feel free to ask questions anytime, okay? This rule that we had before is parsing the literal size followed by this float parser. We would like this rule to also synthesize a 42.5. And so we want to be able to explain to our rules what it is that they're going to synthesize, what it is that they're not going to synthesize. All right, if you've used V2 before, we don't have grammars anymore. We just have composition of rules. Grammars were kind of a wart that was added in order to take care of lifetime issues with composing rules and keeping some things around due to the way that the internals were formed previously. We don't have this anymore, and so grammars you can just not think about if you've worked with V2 before. You can just compose rules, compose rules, compose rules. It's a lot nicer to deal with. All right, let's take a look at some parsers. So the idea here is we're going to take a data stream. We're going to bring that in and parse that into an abstract syntax tree. That's the goal. We want to bring stuff in and have a data structure back out that we can deal with and work on inside of our code. So inside of X3, what do parsers look like? Well, this is a parser that will parse an int. This is one that parses a double. Here's one that parses a literal foo. We can use parsers with the X3 parse API. So I have an input of 1, 2, 3, 4, and I can say parse, passing it a begin and end iterator, and then I can pass it the actual parser that I want it to use. And so this will parse the 1, 2, 3, 4, or any int. If I wanted to parse doubles, then this is a double. So what kind of parsers exist? There are a lot of canned parsers. These are some of them. We have ones that can parse things like int, uint, double, bool, the different types of binary things, of word types. We have literal parsers. This will parse a -42 or an unsigned 82. This will parse true or face or dead beef. The literal parsers all form the same type of thing where you have the parser that will parse anything and then you pass it actually the value they want to parse and now you have a literal parser instead. They follow the same pattern. Here's some of the character parsers we have. So char underscore will parse any character. Here are the literal versions, which is bar will parse bar. This will parse A through Z. This will parse A through Z, the number 8, and then capital A through Z. Character parsers have a special not, so this will parse everything that is not A, and it is more efficient to use this than some of the other constructs that you might want to use. So let's look how we combine parsers, because parsing an int is not very interesting. So if I want to combine some parsers, here I have 86 and a space, and then 123.4.56. I can parse the int. Here's the space. Here's my double. And we use the right shift operator. And when you see that, you read inside of the language, you read it as followed by. And so we read this as, I'm going to parse an int followed by a space followed by a double. Yes?
Does space match literally a single space, or does it match white space in general?
So the question is, does the space here match literally a white space, or the space? And it does. In this case, we're parsing and matching just a space. In a moment, we'll talk about skippers and how we can skip and define skipping of, for example, white space. All right, so there are a variety of different types of operators that we can use in order to compose parsers together. And these are the operators. The first is sequence. So sequence we read as followed by A followed by B. It looks like this inside a peg. And the A followed by the B, in this case int followed by space followed by double, which we saw before, would be able to parse this. Or char followed by the colon followed by int would be able to parse this. We have alternative. Either A or B are allowed. And they're evaluated in list order. This is one of the things about peg versus some of the other types of definitions of grammars that exist. So it gives us a deterministic behavior in peg. So we're going to parse alpha, followed by digit, followed by punct. Any of these things will work. This is going to fail to parse because it doesn't meet any of these. Zero or more, the clean start, instead of putting it after what you're used to seeing, it goes in front because of operators for us. So 0 or more alphas followed by an int would look, all of these would parse fine. 1 or more alphas followed by an int. This is obviously going to fail. I don't have any alphas in front. This is optional. So an optional alpha followed by an int. And so this is going to fail because this is not an optional alpha. This is a whole bunch of alphas that were followed by an int. So the question is, would you do plus minus alpha for optional 1 or more? And optional 1 or more is basically saying 0 or more. So you just use a clean star. Trying to trick me. It's okay. I caught up in sleep last night. All right. The and predicate basically provides look ahead. We can look ahead into the stream without consuming it. Very convenient thing to be able to do. And so if A matches without consuming A, then the parse is good, and it can continue on to the next step. And in case it wasn't clear yet, A and B's up here are parsers or combinations of parsers or composed parsers, right? They're the thing. And so here, an int followed by, and then this is the and predicate, a semicolon. This is going to actually be okay, but this is going to fail to parse because it wasn't followed by the semicolon. The not predicate is just the opposite. So for followed by not an alphanumeric or an underscore, this will pass fine, 40 will not. All right, we have a few additional things that come up a lot when we're writing grammars, and we leave the realm of PEG. There's no PEG equivalent for this, but they're handy, so we've added them in. The first one is difference. And so the idea is I want to match A, but I don't want to match B. I'm trying to parse comments, C-style comments. So this followed by 0 or more characters that are not the ending thing, and then followed by the ending thing. That's a pretty common pattern where you're needing to do this. And so here's a nice and easy way. So this would always fail. Literal obi watanabe followed by, or less the obi-wa. Well, there's no way to do this. And so just kind of be careful as you're writing your difference that you've made something that makes sense. Will actually parse. Okay, expectation is also something that is very different. The idea of an expectation is that you're saying A is followed by B, and it has to be followed by B, always. There will be no backtracking to find something else. If you have an A, there has to be a B right afterwards. Internally, an expectation point gives us a lot of advantages with inside of the parser. We know that that's basically a point in which we can flush any backtracking. We can remove memory that we've been scrolling along and keeping. There's a lot of things that we can do internally as soon as we see one of these. They also are ways for you to say that every time I see a particular thing, it's got to be followed by the other, and if it's not, it's an error. And I would like you to say that there's an error and let me know, parser, and provide some information. Like you can get out where you are. If it's a file, you might want to know what line you're on or what character you're in, things of that sort. So expectation they're really great things. So in the case here, O followed by K, we've got to have an OK. We can't have an ox. And when it says throw an exception, internally it's throwing an exception. We'll look at some of the error handling mechanisms, how you get those back out. So the difference between sequence and expectation is that a sequence is A followed by B. And if you don't have a B, you're going to backtrack and see if there's an alternative that might match it. You might have an A followed by a C. And so that would be fine, right? But with an expectation, if you say A must be followed by B, it has to be followed by B. All right, here's another one, list. It's super common to have lists of things that you are parsing. And so it's really just a shortcut for A followed by 0 or more B's followed by A's. So here would be an example of an int, and there's a list of ints that are comma separated. And so this right here would parse nice and easily. And so lists of things are a very common construct, and so we have the percent that we use for that. Again, A and B are any parsers or composed parsers to do that. All right, so far, good? Great. So let's take a look at some information here and how to put these things together. We've got some input string here in which we've got some values, characters, followed by a colon, followed by some more characters, and they're comma separated. So it kind of looks like we have pairs of things. The right-hand side, we might have quotes, a quoted thing. Joel Falcoul, by the way, is the crazy Frenchman. And he's just proving it, by the way, because he's doing 3 hours of lecture right now. I don't know. So here is our input string. What would it look like to parse this? Well, we want to parse a name, followed by a semicolon. Sorry, a colon. I want a colon. A name followed by a colon, followed by either a quote or a name. And this thing, well, it's a list of these. So I have a list of these things. Now, I've swapped some things out for you. Instead of parse, we're using phrase parse. And down here, I've added this thing called space. What I'm telling it is that now I'm doing phrase parsing, and I have a skipper. And the skipper is a white space skipper. It'll automatically skip white space until until it can't skip white space, basically until the skipper fails. And at that point, when the skipper fails, then the grammar that I've provided to it kicks in. Skippers are interesting things. They're just grammars. You can supply your skipper to be anything you want just by supplying a grammar. Another rule. Yes? Wow, I'll give you a buck later. So the question is, how do we define the name and the quote, space, things like that? We're going to find out right now. So let's look at some rules. Rules allow us to be able to do some things. In particular, they allow us to name parsers, so we can reason about them as name or quote, things like that. Lets us read our grammar in a reasonable way. They allow us to specify an attribute. We would eventually like to synthesize probably something out of this and attach it to the rule. It allows for recursion. It's pretty in my world at least, it's very uncommon to have a grammar that doesn't recurse. So we want to be able to refer to the rules again. Allows us to provide error handling. On error, what is it going to do? An error would be, for example, an expectation point, A followed by B, and I didn't get a B. What is it going to do? We can attach custom handlers when a match is found. So here we go. Name is alpha followed by 0 or more alphanumerics. Alpha and alnum are built in spirit parsers. So we're just using 2 spirit parsers. That's what a name is. A quote. A quote is, well, the beginning quote character followed by 0 or more characters that should say tilde, and LaTeX, of course, ate my tilde, and it made it a space. There's a tilde there, followed by a quote. So we're going to basically grab all characters that aren't quote, and then quote. We only use auto for non-recursive rules. We'll see a little bit later. This is like a shortcut to write all this and just get up and going right away. Yes. Yeah, so in order to make the slide nice and easy to read, there are some explicit usings in here. In this case, this is inside of the boost spirit x3 namespace. Yeah, so the shift operator, eventually this is going to get tainted by a parser, by a type that is inside of the spirit namespace. And then all the expression templates from that point on work nicely for us. So let's take a look at what we do with rules here. So here, I've got alpha followed by alphanumeric. Oh, good, I got my tilde back. And here's our quote version. And I'm going to add this little thing in here, this rule, this x3 rule, and class name. What this is doing is creating a tag for us that we'll never see again, but we need a tag that's unique. And the tags are as we'll see in a little bit later, the tags are the things that are going to allow us to use ADL in such a way to pull a bunch of things together and relate them so we can have some lightweight objects to talk about recursion with and things like that that are not the definition of our parser. They allow us to look up the definition of our parser later on internally. Really don't have to worry too much about it. As a general rule, what you do is you just like create a tag name that's probably the same as your name here. Okay, so this is how I'm going to write my X3 rules. Yeah, the tag name I just talked about. So let's take a little closer look now at what we're going to do.
On the tag name real quick, does that have to be unique in all namespace or just in say X3 namespace?
Yeah, so the question is, does the tag name need to be unique in what namespace? The tag name needs to be unique within the namespace that the tag is defined. And that's what's going to get us the ADL lookup. Yeah. All right, so here we have, getting a little closer to what we want. Our name is followed by our alpha, followed by 0 or more alphanumerics. Our quote is getting a little more complex now. This lexeme, as soon as we have the quotes, what we really want to do once we get quotes is we want to shut off the skipper because we don't want to skip white space anymore. That's what it meant. And that's what lexeme does. It turns this off. Everything inside of here, it's a directive. Everything within this directive, then the skipper is turned off. And then as we leave that, then the skipper is turned back on. And so now this will parse this thing for us. We've now got our rules in here. We know actually what name and quote are, name followed by, and so bam, look at that. So this is a lot more readable. I hope you think this is also a lot more readable. It's declarative than that first craziness that we saw of trying to grab single characters out of a string and figure out what to do with it, right? All right, so we've combined some parsers. We've parsed a little something here. Let's take a look at attributes. So eventually, getting yeah, it was good or no, it wasn't isn't interesting for most people. They don't want to just know that the parse was successful. They want actually the data out of it. So how do we get the result of this parse into a map of string? Wouldn't that be nice? That'd be really nice. So we have this key value map, and now we do something clever, and bam, our key value map is filled in. So let's figure out what the clever thing is that we need to do. So we've been talking about parsers. Parsers have associated with them an attribute type, the thing that they're going to synthesize naturally. Literals will not actually synthesize anything. They have no attribute that they'll synthesize. Primitives will synthesize the thing that makes sense when you look at it. It's pretty obvious. Doubles will synthesize a double, and so forth. Non-terminals, like rules, will synthesize whatever you tell it it's going to be synthesizing. So this non-terminal is going to synthesize an A. How about these operators? What are they going to do for us or to us? So an A followed by a B is a tuple of A and B. An alternative is a boost variant. It's either this thing or that thing. How about these? So 0 or more, 1 or more, or a list of things is a vector of the type of that thing. Whatever A is synthesizing, it's a vector of that. We'll get a boost optional, and predicates obviously have no attribute that they're going to synthesize. All right, so how do we now get that value? Well, it's actually pretty easy. So here I have a parser that's an int, and I've got an int, I'm going to feed it, and I simply provide a reference to the thing to stick it in. So this will parse the int into result. Okay, I'd like to parse pizza into an std string. And I can do that. And the reason that this works is we talk about compatibility. And while we say that the clean star or the one and more, the list all go into an std vector, the reality is that they go into the concept of a container as described by the X3 specification of what that means. And anything that is compatible with that concept then therefore will work. And so a string is compatible with the std vector of char. So therefore, a string is just as valid as anything else right here that could look like one of these container types. How about cosmic space pizza? Well, I could do this. I could have result 1 be cosmic, and result 2 will be pizza. But that's going to become pretty unmanageable pretty fast. So it ends up that looked like a tuple, right? And that's the same thing as a pair. That works for me. And so result here of a pair of strings, and I can put it here as the reference that I'm going to parse into. And now cosmic will go into the first of the pair, and pizza will go into the second. Yes, question?
Okay, let's say that instead you have cosmic pizza, pepperoni, space pepperoni. Then it seems like this will break, or this won't.
Yeah. So basically the question is what happens when you have more stuff continuing on? And what happens is the parse is fine. There's no error in completing the grammar. However, if we looked at iter and iter end, they're not equal, right? We didn't consume all of the input. And so that's different than a failed parse that we might receive back out of the parser.
So let's say that you wanted to do it so that iter and iter end equals. You want to keep on adding it. So instead of having just two std strings, you just put a vector of std strings.
Yeah, so the question basically is what would you do if you want a vector of std strings? If you just had a bunch of these and they kept going on, then that would look like a clean star of this thing, right? And this then would no longer be a result here, but we're going to see in a moment maybe something else that we might want to do. Don't ruin my next set of slides, Vishal. All right. So attribute parsing is where the magic lives in Spirit. And that's enabled through the Fusion library. So at some point, if you decide that, wow, that's really pretty amazing, you want to go look probably at Fusion, which is pretty darn amazing. So let's take a look at some of these things. Here I have a string that's going to be what my name is going to synthesize. So my rule for the name is going to synthesize a string, and my rule for the quote is going to synthesize a string. And my item now, I'm going to actually parse this as an item. Well, that is basically two strings. I know how to do that. That's a pair of strings, right? Name followed by either a quote or a name. So let's take a look at these in detail. Alpha is going to synthesize a character. And the B side, which is 0 or more alphanumerics, that's going to be a vector of character. And how this works out, right, is this is A followed by B, in which these are compatibility rules. This is a character. This is a standard vector of characters, and therefore that could be quite compatible with just a standard vector of characters. It can collapse if the attribute provided to it would allow it to collapse. How about here? Well, literals are unused. So here's an unused, and here's the unused for here. And the center, this is easy enough. This is a vector of characters. And a vector of characters is definitely compatible with a string. So in essence, a tuple of an unused followed by this something and then followed by an unused is just the thing in the middle, right? Quote is a string, or name is a string. So a string or a string would be a pretty useless variant at the moment. We're not going to talk about variants of the same type, okay? And therefore, this could look like just a string. That now brings us down to, we've got this is a string, and this is now a name followed by what works out to be A is a string, an unused, and a string, and that just looks like a tuple of a string and a string, because this was unused. So this looks like a pair of a string, string. Great, because I would like my items to be a comma-separated list. And a standard pair, a list of standard pairs, looks like a vector of standard pairs, which is basically a container of standard pairs, which really is just a map. And therefore, this thing is just a map. And so the magic is nothing. The magic of what do we do that's special in that spot is we just give it a map, a reference to a map, because a reference to a map is compatible with the grammar we had already written.
What is this sorcery? Is this black magic?
Not quite.
It is the first time I've ever seen the fact that a map holds pairs actually be a good thing.
Well, in this case, a map holding pairs, it's a compatibility thing, right? And so the pair is of string and string, and therefore a map is just a container of two strings. All right.
It's really a multi-map.
It really is a multi-map is the question. Let's continue on, and we've got a bunch of slides to get through and run kind of low on time, and I'm here all week. So the rules attribute type is optional. If it's not going to synthesize something, you don't need to put it, and then you wouldn't have a rule attribute. So let's look at an example here. Before we get to the example, just a couple little guidelines. How many people here have used Spirit? Maybe we'll start with that. Okay. How many people here have used any library that uses expression templates or other Boost meta-programming libraries of any sort? So, okay, good. That's the whole room at that point. So you will already be accustomed to the fact that the compiler is going to spit out copious amounts of crud that you don't understand. And eventually you will hunt through it and you will find something that's useful, but you probably won't do that. You'll probably give up. So Spirit uses static asserts all over the place when things are bad. And it tries super, super hard to tell you what's going on. But unfortunately, you have to find it in the compiler's spew. And how you find it is you search for 4 asterisks in a row. And it will have a line number along with the static assert and the file. And you go there. And if you're in an IDE or Emacs or something like that, you can pull up the file and there will be a narrative that tells you exactly why the compiler was static asserting at that point and what you probably need to change in your grammar. So as opposed to just throwing up your arms and saying, I have no idea, why did I ever start this project? All right, so things are hard, concepts will make it better. There we go, that's my... So start small. Alternatives in your grammar are a natural place to break things up. Just start with like one of those and work on it, and then add another one, and then add, or just work on each alternative at a time to make sure that they work. Start small and build up until you get experience using Spirit. So you're going to start from the leaves and work your way up. Compose and test. Compose something, test it. Compose something, test it. Do a lot of that. Don't write your whole grammar that's pages and pages long and then like wonder why it doesn't work. That's just, you're going to be sad. Test early and often. Nobody ever listens to this, but I'm going to say it anyhow. deal with parsing first, and then deal with attribute synthesis second. All right, so you want to worry about the parser first, and then worry about the attributes next. Don't try to do both at the same time until you get some experience with this stuff. Allow the natural AST to fall out. Your grammar has an AST. Don't fight it. It wants to generate some data structure for you. Let it do that. Let it make the data structure. You can already see that we're going to be able to manipulate the container types all we want within certain bounds, but don't fight it beyond that. Instead, what you do is you have an AST that comes out and you transform that to something else. That is so much easier and more efficient than putting in semantic actions everywhere when the parse is true, do something action-wise. That now no longer is a nice declarative grammar. That's like procedural stuff crammed into a declarative grammar. It's nasty. And then refine your grammar in your AST. So let's look at a JSON very quickly, parser. They're nice and easy. So if you're not familiar with JSON, I would be surprised. Joel tells me that everybody and their dog is. So, and JSON has objects. They're within curly brackets. The object has basically pairs in which the first is a string and the second is a JSON value thing. JSON values can be strings, or they can be objects, or they can be Booleans, or they can be numerics, or they can be with the brackets and then lists of things. They can be null. So the idea, as you can see very quickly, of course, a list would be a list of JSON value types. This is a recursive data structure. Not a complicated one, but one that we can actually create some amount of detail with a bit of type information along the way. What would an AST look like? Well, this is one potential or possible AST for this. We're just going to say that a string is an STD string, and a double is a double, and a float, because we're going to somehow deal with those differently, as a double. That when we're dealing with integers with inside of our JSON thing, it's an int64. Boolean type is a bool. Null is just an empty struct. I'm going to predefine pre-declare a value. And then I'm going to say an object is a map of string to value. And an object member, therefore, is the value type, the thing that's inside here. And an array is, I'm going to use a boost stable vector for a reason that doesn't matter for this talk, of values. This could just be an STD vector, by the way, for what we're doing right now. All right, so you can see the recursion is starting to begin right now. So what is value? Value is an X3 variant. An X3 variant, you can think of it like a boost variant, except a boost variant is not an object. We don't have an object, we have a type def, which is super annoying because I can't actually say this with the type def and then use it. But here I can. And so how this works out is now I can inherit from X3 variant, and now value is going to be able to contain either a null or a bool type or a string type or an int type or a double type or an object type or an array type. Okay, it's one of those things. That's what this value holds. I'm going to pull in some. I'm going to pull in the constructors and assignment operators from the base so that I can just assign one of these and make it work. If it's default constructed, it'll be null. A little bit of trick in order to make this work for doubles for any floating point type. And then a little more trick in order to make this so that if I have any integral type or an enum, it will work out to be an int type when I create one of these. This is all kind of unimportant stuff in order to construct them. Yeah.
Or did you say you should focus first on parse or lensing and then later worry about
He was listening really well. Yes. So the question or the comment is, didn't you just say that you should focus on the parser first? Yes, I did. But we don't have time to focus on the parser first and then the attributes, so we're going to do it all at once. And this is what falls out naturally, by the way, of the parser. So good catch. So at the top level, a value is going to be a variant of one of these. I want to deal with grammars because grammars are just like nice packages. They make me feel good. But really at the end of the day, a grammar is nothing more than a bunch of rules composed together to make some higher level rule that I can think about. And so this is what I'm going to do in the code. Here is that tag that I'm going to use. It's a JSON class. So in my rule, JSON class. And it's going to synthesize a JSON value. That's this thing. It's going to synthesize one of these, a variant of any of these things. Boost spirit declare. So how X3 works, and in order to speed up compile time just greatly, it uses ADL for lookup for things that it used to use for making instantiations of stuff all over the place. And as a result, we have to tie a bunch of things together. And what holds the stuff together, this is probably detail that you don't care about for using it, what holds the stuff together is this tag. So JSON class is the tag that's going to hold all the things together. Here it is here. It's going to show up in some more places. And if you say boost spirit declare JSON type, this expands out to be about like 3 or 4 lines to take care of some stuff for you. You can write those 3 or 4 lines, or you can just type that in the declare. So here are the naming conventions if you want to just use the nice macro. Your identifier, your ID is going to be identifier underscore class. Your rule is going to be identifier underscore type. The definition of your rule is going to be identifier underscore def. And then you're going to just refer to the rule in general as identifier. So that's what we had right here. So here's our JSON type. This is the rule type. All right, so we're also going to have a value class, an object class, and a member pair. These are the things that we saw a little while ago. And now, what are they? Here are the rules. Well, the value type rule is going to create a value for us. An object type rule is going to synthesize an object. The member pair, an object member pair, an array is going to synthesize an array. I can now create my rules, which is of the type of whatever the value type value, the object type object, and so forth. And I'm giving them this string, and the string is just in debug mode. You can actually have, as it's parsing, spit stuff out of what it's doing and where it's backtracking stuff, and now you know where it is. These are going to be the lightweight things that are used in the system. This is what we're going to use in order to refer to these rules from this point on. And here we see the first one. The definition of a value is it is a null value or a bool value, or it's a Unicode string, or this is an integer because it is not followed by one of these, or it's a double, or it's an object, or it's an array. So what is a null value? Well, a null value in JSON is literal null. And when we see the literal null, we would, which as you know, literals do not synthesize an attribute, we would like it actually to create an attribute for us. X3 ATTR, when this will parse or consume nothing out of the stream, but it will generate the attribute. And so this is going to generate a null type out. We saw an int. What is an int? It's going to be an int64 parser. And bool is just going to be the bool type parser. What is an object definition? Well, an object definition is a curly bracket followed by an optional list of member pairs that are comma separated, and then ending with a curly. Well, what is a member pair? A member pair is a Unicode string followed by a colon, followed by a value. Right? So we see our first bit of recursion right here. What is an array? Well, an array is simply a left bracket followed by an optional comma separated set of values, right? Followed by a right bracket. All right, we just defined null, the int type, the floating point type. We dealt with the bool type. We've dealt with an object and an array. The only thing we haven't dealt with is the string. So if we weren't being fancy in trying to deal with Unicode strings, we would just do what we've been doing for strings, which is 0 or more chars, right? And we would call it good, and we would have a grammar that everybody could read and would be done with, and it'll just work for JSONs with, you know, some caveat of we don't like Unicode. I mean, you know, they did put spaceships up on the moon without Unicode. It happens. All right. So when you get to this point here, you can say boost spirit define and list your rules within the namespace. This does that pulling things together with the tag for you because we're going to use the naming convention, right? And it does a little bit more work for you and call it good. All right, let's look at what the Unicode string looks like. Same type of stuff. And a spelling error. Interesting. So here is the Unicode string. It's kind of weird. And it is, let's start with this double quoted. What is a double quoted thing? It is shut off the parser, excuse me, shut off the skipper. It is a quote followed by 0, and it's, notice, we are using an expectation point at this point, followed by 0 or more escaped characters, or it's one of these, and ooh, what is this weird thing here? Well, if you see something in brackets out at the end, this is a semantic action. It's the things we want to stay away from generally when we're writing grammars until like it's last resort and we don't know another way to do it. At this point, what we're saying is, when this parse is successful, execute something. What is the something? Well, it's this lambda. And the lambda is receiving the context of the parse at this point in time. And within the context of the parse, there's this thing called val. Val happens to be the current attribute that you're in the middle of the parse. And we're just going to stick on the end of it the attribute of the context. So this is the value of the context. It's the thing that's coming out of here. And the attribute is the one that it just succeeded on. What is escape? Escape, or char escape, is the escape followed by whatever this escape thing. And the escape thing is going to be a U followed by a hex 4. Well, what is a hex 4? We're going to define a hex 4 as being an unsigned int parser that is unsigned characters, 16 of them, 4, 4. And here we also have decided to stick on 2 more semantic actions to take care of this. The first one is this push escape, which is going to take and look what is it that we've got and push back the appropriate thing into the UTF-8 thing that we're building up. And then push UTF-8 is going to take care of sticking it in the rest of the way. So occasionally you will end up possibly with semantic actions, but it's only in really, really weird, odd cases. Most of the time you will end up parsing without any weird, odd cases. At the end, how do we parse this thing out? Well, we can call phrase parse. We give it the begin and the end. We give it our grammar. That came out of here. And this is space type. And where we would like to parse it into. We can catch any exceptions at this point for failures and then handle them appropriately. So we wrote a JSON parser with really very few set of lines, and it is probably pretty understandable. Yeah, what's the question?
Excuse me, but what if you wanted to actually, instead have the, we would go back to the first one, oh no, one that we just changed.
This one?
No,
This one?
no. The one that was before we did that.
That would be that one.
Yeah, so let's say that you wanted to check
Yep. So you would check parse except to see whether or not your parse was successful. And you can then check the iterators and compare them to see whether you consume the whole thing. Now, the time that you throw is when there is an expectation point that you didn't meet. And then at that point, bad things occur, right? And you can then deal with them, whether there's an on error. If there's an on error handler, you might want to print out the line number or such or store that somewhere. We've got just 5 minutes, and I'd like to just do one thing here. This question comes up a lot, and might as well deal with it a little bit. This is just a quick overview of a bit of stuff about Spirit, right? But a lot of times what we're trying to do is parse inside of your own data structure. I've got my own data structure that I'd really like to parse this information into. How do you do that? Well, if you have your own structs, remember, Spirit wants to be able to parse things like this followed by that into a tuple of something. And if you could figure out how to make your struct look like a tuple, life would be great. And it ends up that Fusion does that for you in all kinds of different ways. And you can say, boost Fusion adapt struct, the struct I would like to adapt, and which of the elements within the struct you're adapting, or the members. So signed has got this signed, it's a char type, and an operand, which is an operand. And so I can say Fusion adapt struct, the thing I'm adapting, and each of the members I want to adapt. You don't have to adapt all of them. And which order you would like to adapt them. You could even adapt them multiple times if you wanted to, or leave some out, or put some extras in. And really what it's doing down underneath is it's creating a tuple of references to that type, of whatever the member type is. And that tuple that it's creating of those references is getting tagged in such a way that at compile time, it can find it when it sees one of those types. It finds the definition of what it is, and it plugs that in. So what do? You adapt it, and you just give it a reference to your data type, and bam, it fills it in. And so we've only dealt with, so far, in our little bit of JSON, parsing a variant or containers, things that it already understands. But for your own types, you can adapt them. If you have your own type that just has methods to get to private data, not a problem. Again, Fusion can adapt getters and setters for members so that when it sees those, it will actually do that too. Clearly not as efficient as being able to directly access and parse into your data structure, but still pretty good. All right, we're basically out of time. Oh, I have 2 minutes? Oh my goodness. What am I going to do with 2 minutes? Okay, I'll take a few questions. Go ahead.
So how does this JSON parser perform relative to other parsers?
So that's a great question. How does the JSON parser perform in regard to other parsers? There are a bunch of parser frameworks out there. I'm sorry, a bunch of JSON parsers out there, and there are a bunch of benchmarks. And if you go to the thing that fell off the end, that is horrible, Kiera Labs. If you go to Kiera Labs and GitHub, the JSON parser is on there along with some benchmarks. And you can take a look at those. Generally speaking, we actually haven't ran it against X3. The V2 stuff, not so much. It didn't perform really great. And the reason it doesn't perform super well has to do with the internals of how variant works and recursive variant in particular, and the way move works with recursive variant things. Which is why there's an X3 variant now, because we have a different idea of what it means to do a move. And it's made for performance. So we'll rerun those, we'll have an idea. The JSON thing that is there is really interested in trying to figure out how to make JSON objects look like they would in Python or JavaScript within C++. And so you could just deal with them, which that's a harder problem than parsing. So the question is the whole parser generated at compile time? It is. So the whole parser is generated at compile time. What you're writing are expression templates. And so at compile time, it is taking those types and it is generating things and combining things and generating things and combining things until at the very end, bam, you have your parser generated. See.
X3 part of Boost 159.0, or is it a candidate for Boost inclusion with status?
Great question. So it is, X3 is being shipped with Boost since 1.5.6. It has been in as a separate line. And you can look at the Spirit documentation to see how to enable it and to use that. So by default, you'll get V2. If you want X3, you can enable X3.
Why isn't there a Unicode parser?
Why is there not a Unicode parser? There may be a Unicode parser at some point. The reason that there isn't a Unicode parser is there's currently a belief to try to keep everything as thin and slim as possible. And V2 kind of got out of hand, and we would like X3 not to. But Unicode is one of those that we're thinking that we probably should just write one and have one. So we're out of time for the session. I'm happy to take questions. Feel free to come on up. But I've got to start shutting things down. Thank you very much.